It's a pleasure to introduce the next plenary lecture by Professor Bernd Sturmfels. He is a professor at the University of California at Berkeley, and his contributions is what in Brazil we used to call multidisciplinary, right? So he works in algebraic geometry, as discrete optimization, and has several many very deep contributions on these subjects. So today he will talk about convex algebraic geometry.
Okay, thank you very much. So it's a great pleasure to be here. So I'd like to tell you what convex algebraic geometry is. The title comes from a project I'm involved in with other mathematicians and engineers called Semi-Definite Optimization and Convex Algebraic Geometry, although in this talk I will emphasize the geometry and the algebra a little bit. And I will jump right in. So convex algebraic geometry is the marriage of real algebraic geometry over the real numbers, with optimization theory, convex optimization theory. And I'm going to start out with some very simple example. Let's consider the red convex body in the plane. This is a curve of degree 3 in the plane. So it's given by a polynomial of degree 3. The black part is also a part of the curve. So if you write down this cubic polynomial, you see the red convex curve, which we would be interested in optimization. But in addition, there are the other black parts of the curve out here. And so let's think about the problem of maximizing a linear function over this red convex body. So suppose we don't know anything, then what we'll do is we'll use calculus, right? So in calculus, to optimize a function, we calculate the derivative, and then we look at all the critical points, all the roots of the derivative, and then we select the root of the critical point that we like the best. So for example, let's suppose we want to maximize the northeast linear function over this body. Then we pick up we count critical points. So there's 1, 2, 3, 4 critical points in the real plane. But it turns out there are 2 more imaginary critical points. So if you write down the equation for the critical points, there are 6 critical points, 2 red critical points that we would be interested in optimization, 2 additional black critical points, and 2 complex critical points. Now this curve, as it stands, it's an elliptic curve, right? It's a smooth cubic curve in the plane, so it has an algebraic life as well. Let's look at the dual picture. Now, duality is very important, both in projective geometry and in optimization theory. And down here you see the same picture in the dual plane. Now, the dual plane, the points in the dual plane correspond to lines in the plane up there, and the lines down here correspond to points up there. The dual curve, the points on this dual curve, are exactly the lines that are tangent up there. So for example, here we see the dual convex body in red. So these are all these points here correspond to lines that are tangent up there. And likewise, inside the picture, we see this black part of the curve. This parameterizes lines that are tangent over there. So we have a curve and the dual curve. There are 3 special points down here. The dual curve has 3 singular points, and they correspond to the asymptotes over there. So this picture, again, in the upper picture, we have a curve of degree 3 and class 6, as the geometers would say. And the dual picture down here has degree 6 and class 3. And this curve has degree 6 because if we cut it with a line, then there will be 2 red intersection points, the one the optimizers would care about. there are 2 black intersection points. In addition, there are 2 complex imaginary critical intersection points. Okay, so now that everybody is here, what I like to do is I like to spend about 20 minutes on a very, very simple example. I like to discuss the ellipse with you. And by the ellipse, I mean the multifocal ellipse with m foci. So I fix points in the plane with coordinates ui, vi, m points in the real plane. And I also fix a positive radius d, so a positive number d. And by definition, the m ellipse is the curve consisting of all points x, y, whose distance sum to the m given points is d. So I look at all, I fix some foci, I look at the sum of the distances to those foci, and I require that that's constant. So it turns out that this is a convex algebraic curve. Now everybody is familiar with the 1 ellipse and the 2 ellipse. So the 1 ellipse with 1 focus is called the circle, and the circle is an algebraic curve of degree 2. The 2 ellipse is the ellipse, right? So the classical ellipse has 2 foci, and that's an algebraic curve of degree 2. Here's a picture of the 3 ellipse. So again, the definition, I plot 3 black points in the plane, and I fix a radius, and then I draw all the points that have a constant distance sum to the foci, and it turns out that the 3 ellipse is an algebraic curve of degree 8. If you write down the unique up to scaling irreducible polynomial that vanishes on this blue curve, it turns out to be a polynomial of degree 8. Well, let's see how this continues. So here's an example of a 4 ellipse. Of course, you know, if you make the radius small, it doesn't have to contain all the points, right? So the radius could be big or small. And it turns out the 4 ellipse is an algebraic curve of degree 10. So again, the irreducible polynomial that vanishes on this blue curve has degree 10. And the last example, here's an example of the 5 ellipse. So the 5 ellipse is an algebraic curve of degree 32. And so one thing that you might think about, maybe the students, is how does the sequence continue, right? So how does the sequence 2, 2, 8, 10, 32 continue? And I'll give away the answer in 10 minutes. Here's a different picture. It's kind of a heat diagram. So here is the, again, I have 3 points in the plane, and I draw the various ellipses as the radius varies. So I vary the radius d, and what you can see in this picture is that these curves, they tend to be smooth unless the curve actually runs through one of the points. So when the radius is special so that the ellipse actually runs through one of the points, there seems to be a singularity. Otherwise, these curves are smooth. And here are a couple questions. So the first question I asked already. So what is the algebraic degree of the M ellipse? What is the degree of the unique up to scaling irreducible polynomial that vanishes on this curve? And how do you write down its equation? Is there a convenient way of writing the equation of this polynomial? Now, as you can see, as you make the radius smaller and smaller, there's a special point, right? At some point, the ellipse shrinks to a single point, and then if you make the radius even smaller, it becomes empty. So this special point has a name. It's a very classical object called the Fem Avaible point. And it's of interest in facility location problems and optimization. So it's the unique point that minimizes the distance sum to the given point. So maybe these are 3 cities, and the question is, where should you build a power plant to supply the city? Well, maybe a good location might be the point that minimizes the distance sum to the given cities, and that's called the Fem Avaible point. And you might ask, how do you compute or represent this point? Okay, so let me give away the answer to the second question in the example. So the way to write down the equation is in the following form. So in the form of an LMI representation. So the engineers call this an LMI, a linear matrix inequality. And so what is this matrix? So I fix the three foci, the origin, 1, 0, and 0, 1. So this is an 8 by 8 symmetric matrix. And the entries of this matrix are either 0 or they are linear, affine linear expressions in x, y, and d. So this is a matrix with a symmetric matrix with linear entries. Now, if for fixed d, x, and y, this is a real symmetric matrix, and there's a miracle about real symmetric matrices, and the miracle is that all the eigenvalues are real. Okay? Now, if the eigenvalues are all non-negative, I'm going to call this matrix positive semi-definite. So that means all the eigenvalues are real. And it turns out the ellipse consists of all points, x, y, where this happens, namely where this 8 by 8 matrix is positive definite. And this is illustrated in this picture. So I have these 3 points. Now, this picture is a picture of the xy plane. And if I pick my point xy here inside the black curve, then I get an 8 by 8 matrix where all 8 eigenvalues are positive. Now, as I go to the boundary, on the black curve, one of the eigenvalues becomes 0, and 7 of the eigenvalues are positive. And then over here, we have 7 positive eigenvalues, 1 negative, 6 positive, 2 negative, and so on. Right? So this is the division. This picture shows the division of the plane according to sign patterns of the eigenvalues. Well, in this entire picture, this is the irreducible curve, which is the 0 set of this polynomial, namely the determinant. So if I take the determinant of this matrix, I get an irreducible, for fixed radius d, I get an irreducible polynomial in x and y, and the algebraic curve in the real plane is this multicolored picture. So maybe in geometric language, so really what we're interested in is this convex curve, the ellipse, but what the algebraic description gives us is the Zariski closure. So the Zariski closure is the red, green, and blue stuff. So these 4 pieces together, this is an irreducible, the real points of an irreducible algebraic curve of degree 8. And the equation is the determinant of this matrix, but we get more. We get the description of this convex set here by an LMI, a linear matrix inequality. It's all the x and y's that make this matrix positive definite. So that's how I aim to write down the equation of this curve. Now here's a 3-dimensional picture. It's again the same picture, but now I vary d as well. So we could look at x, y, d in 3-dimensional space, satisfying this inequality. The distance sum is at most d. So this would be the interior of this convex cone here. But then in addition, you have these other branches out here that corresponded to the red, green, and blue stuff in the previous picture. And so there you can see again sort of a feature of convex algebraic geometry. We have a convex object that we might be interested in optimization theory, but the algebraic description forces us to pick up these additional branches. So these additional pieces of the surface, they come by the Zariski closure. They come by drawing all the roots of this polynomial in the plane, and we have a linear matrix inequality that divides this space according to the signs of the eigenvalues. Okay, so here's a slightly more realistic picture. So finally, the algebraic truth revealed. So this is a picture of the 5 ellipse as an algebraic curve. And well, the ellipse is really, I picked the radius so that this small, tiny convex body in the middle, this is the actual ellipse, right? So I picked you have 5 foci. These are the red points. There's a very, very small convex curve in the middle. This is the ellipse. And all the rest of it is the Zariski closure. So all the rest of it, so there is a 32 by 32 matrix with linear entries. And these are all the points where the determinant of this matrix vanishes. But we're primarily interested in this convex body in the middle, which is the ellipse. Now, I'd like you to notice a couple things about this curve. So this is a curve of degree 32, but this is a curve that's visibly of degree 32. It has the so-called Helton-Vinnikov property. And by this I mean the following. Every line that passes through the convex region, so I take any line that actually meets the convex regions, it meets the curve in only real points. So this curve, again, so if I draw a line through the ellipse, and I intersect it with the curve, and I calculate all intersection points with the complex curve, I solve the equation, it turns out that every root is real. So the same miracle that we saw a minute ago happens. All the intersection points will be real, and we say this is a Helton-Vinnikov curve. And we saw the same here. So this is has the same property. It's a curve of degree 8, but it has this Helton-Vinnikov property. If I draw any line through the ellipse, it will meet this complex curve in 8 real points. 2 black points, 2 green points, 2 blue points, and 2 red points. Okay, so one question is, how do I get this kind of linear matrix representation? I'm going to give 2 answers to this, maybe for the algebraic geometry and students in the audience. Of course, this is a line bundle on the curve, right? So I have the curve. On the curve, I have the kernel of this matrix, which is a one-dimensional vector space. So what I give you in this picture is a curve together, with the one-dimensional vector space. So really, this is all about constructing pleasant line bundles on algebraic curves. Okay, so what comes after 32? Well, here's the answer. So it's a little paper we wrote. So the polynomial equation defining the M-ellipse has degree 2 to the m if m is odd. So that happens for the classical circle, for example. But if m is even, then there's a correction term. So if m, the number of foci, is even, then we have 2 to the m minus the central binomial coefficient m, choose m over 2. So this is the general sequence, 2, 2, 8, 10, 32, and so on. Now, as I indicated, we can express this polynomial as the determinant of a symmetric matrix of linear polynomials. And of course, this representation extends. So I gave the example of ellipses in the plane. But of course, you could look at ellipsoids in arbitrary dimension. You could look at the weighted version, right? So you might argue that one city is more important than another city. So you don't want to take the distance sum when assessing the distance to the power plant. Maybe you want to give a higher weight to one city over another city. So there are many variations. And there's a little paper with Ni and Parillo called Semi-Definite Representation of the K-ellipse. And what I like to emphasize here, so this was published in a volume of the IMA, that's an Applied Mathematics Institute in Minnesota. And maybe sort of by way of opinion and philosophy, so Robin Hartshorne yesterday said that the algebraic geometry in the 19th century was very concrete. In the 20th century was very abstract. And maybe, so that's my personal view, in the 21st century will be applied. So I think of algebraic geometry as moving, a part of it moving towards applied mathematics. If you're a member of SIAM, the Society for Industrial and Applied Mathematics, just last week they started an activity group in algebraic geometry. So if you're a SIAM member, please join the SIAM activity group in algebraic geometry. Now for the students, there's still lots and lots of questions even about the ellipse. So the ellipse, of course, is a fairly simple object, but there are quite a few things I don't know. So for instance, I don't know what's the genus of the M-ellipse. What's the structure of the singularities? Now if you look at these pictures, there are some visible real singularities. So if you look at some of these intersection points, so they have to do, when you write down the sum, the distance sum, you can replace any of the square roots by minus the square roots. And so there's some obvious singularities that you see. But in addition to that, there are some sort of non-obvious singularities in the complex numbers. So I don't completely understand the singularities, and I do not actually have a formula right now for this genus as a pinched Riemann surface. Now here's one that's very embarrassing. I don't know the algebraic degree of the Fem Avaible point. I don't know even for 5 cities. So suppose you have 5 cities in the plane, and you calculate the Fem Avaible point, the unique point that minimizes the distance sum. Then the coordinates of this point will be an algebraic function of the 5 given points. So for example, if the 5 cities have rational coordinates, then the Fem Avaible point has 2 coordinates which are algebraic numbers. So they have a degree, the degree of the minimal polynomial, and I don't know the degree. So for 5 points in the plane, I know that the degree is more than 5, so you cannot write down in radicals. It's less than 32, but I don't know what it is. So that's actually an open problem. Now here's one that's very important for applications. So if I have an LMI representation of a polynomial, it can happen, in fact happens here for even m, that the degree of the determinant is smaller than the size of the matrices. Now this doesn't happen in projective geometry. So in projective geometry, if you write homogeneous polynomials into the matrix, so if you look at such a matrix, if they're homogeneous polynomials, well, the determinant will have the degree equal to the size of the matrix. But these are non-homogeneous polynomials, so usually there's a collapse in degree. The degree of this polynomial will be smaller. And in that case, it would be nice to transform the matrix to a different, smaller matrix that has the same determinant. Now, in general, this can't be done, or we cannot hope to do this, right? So in theoretical computer science, for example, people try to give such a determinant representation for the permanent. There's something called the determinant complexity of a polynomial. That's the smallest size of a matrix. And, well, you know, if you could do this systematically for a special polynomial called the permanent, you'd be rich and famous in theoretical computer science. So we cannot hope to do this in general. But for these classes of geometric problems, say associated with ellipses and ellipsoids, we might hope to have a kind of reduction technique. So these are some open questions about the ellipse. Okay, so I'm 23 minutes into the talk, so maybe this would be a time to give some general definitions, and I'm going to tell you now what is semi-definite programming. So before I do that, let me define a spectrahedron. So a spectrahedron is the intersection of the cone of positive definite matrices with an affine linear space. So if you look at the set of positive semi-definite n by n matrices, this is a full-dimensional cone in the n plus 1 choose 2 dimensional space of matrices, and it's a convex cone. Now this convex cone is not a polyhedral cone, so if you look at it from far, it looks like an ice cream cone. So the picture, if you look at the positive definite cone, if you look at it from far away, it looks like a nice smooth cone. But just like with the ice cream cone, as you get closer and actually eat the ice cream, there are lots of singularities, there are lots of little bumps on the ice cream cone, and the same happens for the semi-definite cone. So the semi-definite cone is not a polyhedral cone. It looks round when you look from afar, but if you look closer, there are lots and lots of singularities, and that's where all the action is. All the actions, as I will try to argue, is in the singularities. Now, the algebraic representation of a spectrahedron, as I said, is called an LMI. It's a linear matrix inequality. And semi-definite programming is the computational problem of maximizing a linear function over a spectrahedron. So a spectrahedron is the intersection of the positive semi-definite cone with an affine linear space. The intersection is a convex body. And then if you want to maximize a linear function over this, this is called semi-definite programming. Now here is a picture of such a spectrahedron. So we are in the 6-dimensional space of symmetric 3 by 3 matrices. So I take a symmetric 3 by 3 matrices, I cut it with a 3-dimensional plane. So the intersection of this 6-dimensional ice cream cone with the 3-dimensional plane is this yellow object. So this yellow convex object is a typical example of a three-dimensional spectrahedron. So this is the 3x3 matrix, a three-dimensional family of positive definite 3x3 matrices. And semi-definite programming means optimizing a linear function over such a yellow body. Now, this is a very, very important class of optimization problems. The first thing to notice, it generalizes linear programming. So what's linear programming? Well, linear programming is optimizing a linear function over a convex polyhedron. What's a polyhedron? It's the intersection of the positive orthant with the linear space. Now, if you take a linear space here consisting of diagonal matrices, then you get linear programming, right? So linear programming, by definition, is semi-definite programming for diagonal matrices. Or put it the other way, semi-definite programming is a non-abelian version of linear programming. Now, this non-abelian version, semi-definite programming, is very powerful because it expresses many, many more problems. So many, many more problems, especially in engineering, can be modeled with semi-definite programs rather than linear programs. So passing to the matrix version gives you substantially more expressive power in modeling optimization problems. However, the solution methods for solving a semi-definite program are very similar to that of linear programming. So in linear programming, often nowadays people use so-called interior point, numerical interior point methods for solving these problems, and the same methods apply here. So there are efficient algorithms both in theory and in practice for solving semi-definite programs. So that's why a lot of people in the applied domain are interested in this. Now, here in this picture, I've drawn the elephant ears again. So this red stuff is a risky closure, right? So the yellow body is the actual spectrahedron given by a symmetric 3x3 matrix. But then, if I look at all the zeros of that cubic polynomial, I get this cubic surface. So the cubic surface here, these are the other stuff, and it goes on. It's unbounded. But in optimization, we're primarily interested in this convex body. So this convex body, actually, there's 4 singular points. It looks like a tetrahedron. There are 4 isolated singular points. Between any 2 singular points, there is actually the straight segment that lies on the body, but it's smooth. So it's like imagine a tetrahedron, but it's rounded out, over the edges to form a nice convex body, but the 4 vertices are still singular points. Okay. Let me say a few words. Yeah, maybe let's stay with this picture for another minute. So, so this is a space of 3x3 matrices. So inside the yellow body, all 3 eigenvalues are positive. On the boundary, there are 2 positive eigenvalues and 1 zero eigenvalue. And outside, we get negative eigenvalues. But at these singular points, the rank drops to 2. So on the smooth points of the boundary, the rank is 2, and drops to 1. So there are 4 matrices where the rank drops to 1. And you can see that when you optimize a linear function over this yellow body, 2 fundamentally different things can happen. Either the optimal solution is at a smooth point, meaning the optimal matrix has rank 2, or the optimal solution is at a singular point. The optimal matrix has rank 1. Now, from an engineering point of view, which would you rather have? Is it better to have the optimal solution at a smooth point or at a singular point? Well, the answer is it's much preferable to have the optimal solution at a singular point. I'm going to give you 2 reasons for this. The first reason is think about sensitivity analysis. Think about varying the cost function. Well, this is a non-stable optimal solution. If you wiggle the linear cost function just a little bit, right, the optimal solution will move. On the other hand, if the optimal solution has a singular point, there's an entire cone worth of linear functions that get optimized there. So this is a stable solution. The other solution, engineering applications. So many of you are participating in the compressed sensing class. In engineering applications such as compressed sensing and many, many others, it's low-rank matrices. What people want is low-rank matrices. So they have the most insight in computer science, for instance. Combinatorially hard problems often have relaxations as semi-definite programs, and these relaxations are exact if and only if the optimal solution is a rank 1 matrix. So in applications, these are the kind that you want. Let's look at this difference a little bit more precisely, algebraically. So let S be a spectrahedron. It's given as the intersection of our cone of positive semi-definite n by n matrices with a general m-dimensional linear space, and we're optimizing a linear function. So n is the size of the matrix, m is the dimension of the space. Now then the optimal matrix will have some rank r, and it turns out that this rank of the optimal matrix, it cannot be too big and it cannot be too small. So this inequality says, so if you know n, the size of the matrix, and m, the dimension of the space, then r as a bound is bounded above. So this says r is not too big. This one says r is not too small. This is a lower bound on r in terms of m and n. In fact, these two bounds, they're known as the Pataki inequalities, they're actually the same inequality. So if you think back to the duality that I indicated, so there's convex optimization duality, which in this context is the same thing as projective algebraic geometry duality. So if you apply duality, it turns out these two things are the same inequality. Okay? So this says the rank of the optimal matrix lies in an interval that's given by m and n. Now, if we fix the rank, it turns out that the optimal matrix, the entries of the optimal matrix, are algebraic numbers over the field of the input data. So if you specify the semi-definite program, so you write down a bunch of matrices that specify the problem, and let's say the entries have rational coordinates. Again, the same question. What is the algebraic degree, the intrinsic algebraic complexity of the optimal point? The algebraic degree of the optimal solution. Well, it turns out that's a function, is given by a function phi that depends only on m, n, and r. And there's a nice geometric description. This phi, m, and r is the degree of a certain dual hypersurface. And there's an emerging literature on this subject. So there was a paper on algebraic degree of semi-definite programming, and there was an improved formula, and so on. So this gives you an exact formula in terms of m, n, and r for the degree of the coordinates, the algebraic degree of the coordinates of the optimal point. So one way to think about this is an intrinsic algebraic complexity measure for the optimal point of a semi-definite program. Now, why might you care about this in an applied context? Well, in linear programming, there are two algorithms, right? There's interior point methods, but there's also the classical simplex method. Right? There's a classical algorithm where you walk along the edges of the feasible polyhedron, and that shows you at the end of the day, in a linear program, the degree is 1. The optimal point has rational coordinates. Now, even if you use a numerical method for solving a linear program, you can round, right? You can round to the nearest rational number. So this opens up this kind of study opens up the possibility of rounding, quote unquote, rounding in semi-definite program. Let me stay though with the pure math. Let me give you a little example. So this I call the Cayley example. So I want to illustrate that phi of 331 is 4, and phi of 332 is also 4. So if I look at a three-dimensional family of symmetric 3x3 matrices, then I can solve the optimization problem in radicals. So I just like to show you, the formula for solving this in radicals, just to sort of illustrate the concept. So here's the formula. So this is a formula for solving 3x3 semi-definite programs in radicals. Let me explain this picture. So first of all, here's our familiar friend. So this is the cubic spectrahedron, the convex body, which is given by such a symmetric 3x3 matrix. So here, together with the elephant ears, indicating the Zariski closure. So even for generic data, this object will always have 4 singular points. So this is a classical theorem due to Arthur Cayley, who was mentioned yesterday. So this kind of surface always has 4 singular points. Here I have the dual surface. So the dual convex body is a very, very interesting body. So it has various pieces. First of all, there are flat pieces corresponding to the 4 singular points. And then dual to this round surface, there's an irreducible algebraic surface of degree 4. And this surface is called the Steiner surface. So this surface was studied by Jakob Steiner around the same time as Arthur Cayley, same Steiner who was mentioned yesterday. And that's a surface of degree 4. Okay, so we have the cubic Cayley surface, and dual to it, we have the quartic Steiner surface, and then we have these 4 planes, right? So here's the picture, you know, the planes are dual to the 4 singular points. Okay, so ready? Let's solve this in radicals, okay? So somebody gives me a linear functional to optimize, you know, over this convex body. So there are 2 possibilities. Either the optimal solution will be a rank 1 matrix. That means, you know, my linear functional came from this coin, right? So you build this body by taking 4 coins and then you make a tetrahedron out of 4 coins and then you round it out. So, well, what happens here? Well, I write down the critical equations. I write down the Kuhn-Tucker equations. I type them into Mathematica or Maple or Singular or Magma. I eliminate all but one of the unknowns, and I get one equation in one variable. Now that equation in one variable has degree 4, right? So because there are 4 of these corners, so I can solve it using Cardano's formula. Let me, quick reminder, right? So everybody knows that there's a quadratic formula. If you have one polynomial of degree 2 in one variable, there is a formula that nobody can remember, right, for writing the 2 roots in terms of the coefficients. There's a similar formula that's even harder to remember for polynomials of degree 4, but if I plug in, you know, I get explicit, you know, expression for these black points in terms of the data. Case 2, well, let's take a linear functional that actually comes from the Steiner quartic. Then the optimal solution will be at a smooth point. Well, then I sweep a plane through, right? I sweep a plane through. So sweeping a plane through, I'm going to say beep whenever there's a critical point. That means I stab this surface with a line, but it's a surface of degree 4. That's a theorem due to Steiner. So therefore, again, you know, I write down the critical equations, I type them into Mathematica, I eliminate all but one of the unknowns, I get one equation in one variable. That equation has degree 4. And I can write down the solution by Cardano's formula. Okay, so this is just a little illustration. I am not saying that you should try to solve large-scale semi-definite programs in radicals. What I'm trying to say is that this kind of geometric analysis for small examples might lead to interesting insight that possibly could be used to design methods for larger problems. Okay, of course, you know, you cannot always solve in radicals, so the algebraic degree in this picture was 6, right? So here's a smooth, was our elliptic curve of degree 3, and then the dual curve is degree 6, and it has the full symmetric group for its Galois group, so you cannot write down such a solution in terms of radicals. Okay, let's state a theorem, okay? So I don't know, this talk probably, I gave you a proof already. I don't think I have a joke, but I have a few theorems to show. So here's one. That's a theorem on aiming to characterize spectrahedra. So one definition, I'm going to say a convex hypersurface of degree d in n space, real n space, is rigid convex if it has the property I indicated. So every line passing through the interior meets the complex hypersurface in only real points. Right? So I have a convex hypersurface of degree d. I draw a line, any line that meets the interior, and I intersect with the Zariski closure with the corresponding complex hypersurface. And if every intersection point is real, I'm going to call that, I'm going to say the hypersurface rigid convex. These things are also sometimes called hyperbolic polynomials. So they come up in partial differential equations, work of Lux in the 50s. So they come under different names. So in this context, they're called rigid convex. Well, here's a theorem due to Helton and Vinnikov, 2006, that says every spectrahedron is a rigid convex body. So whenever you have a spectrahedron, it has this property. Now this first part is actually very, very easy theorem. Let me give you the proof. The way you prove this is you reduce it to the one-dimensional case. So you can reduce this, geometrically to the one-dimensional case. Now what does it say in one variable? In one variable it says, well, you have a one-dimensional spectrahedron, right? The hypersurface is a bunch of points, and they're all real. Well, that's our old miracle, right? The miracle is a symmetric n by n real matrix has only real eigenvalues. That's exactly this statement. So this statement easily reduces to the miracle that symmetric matrices have real eigenvalues. Now this is the hard part. The converse is true for n equals 2. So if you have a curve in the plane that's rigid convex, then it is actually a spectrahedron. You can build a linear matrix inequality. So for example, here we could look at this picture. We could look at a picture like this if we're interested in a convex body like this, and we ask, is this black convex body a spectrahedron? To answer that question, we have to draw the colorful stuff. We have to draw the Zariski closure. Then we look, we pass any line, and we see it has this property. So this is a theoretical proof. So if we believe this statement, it's a theoretical proof that this 8 by 8 matrix exists. This LMI actually exists. Now why is this a hard theorem? Well, because you really need to construct line bundles with good properties. So for the experts, this has to do with theta characteristics and the Jacobian of this curve. So you first prove this for smooth curves, and then you kind of have a degeneration argument to singular curves. So this is a very easy part. This is a hard part. Now the converse is not true in higher dimensions, right? So if you have, for example, let's suppose you have a smooth cubic convex surface in three-dimensional space. Well, it can't be a spectrahedron, right? It satisfies the condition. It's, you can easily draw it, and it's rigid convex. But it's not a spectrahedron because Cayley showed that every cubic spectrahedron in 3 space has 4 singular points. So the converse cannot hold in higher dimensions. But, that's not so bad, because in optimization theory, often what you do is you want to optimize over a low-dimensional body. Often it has a representation in a high-dimensional space that's better. So you might have a complicated convex set in a low-dimensional space, but you can write it as a projection of a higher-dimensional convex set that has a better representation. Well, it's very easy to optimize, right? This projection has a dual linear map that you move the linear functional to the big space. You optimize there. So from an optimization point of view, the following problem is actually more relevant. So is every compact, convex, basic, semi-algebraic set the projection of a spectrahedron in higher dimension? So that's an open problem. There has been some recent progress by Helton and Nie, and they have a theorem that says the answer is yes if the boundary of this convex body, if the boundary of the convex body is sufficiently smooth. So they express it in terms of a sort of curvature condition involving the second fundamental form, but it's really you don't want to have too many singularities on the boundary. So at the present, we don't know, how to approach this problem. One idea is maybe to use a technique from algebraic geometry called resolution of singularities, but we don't know how to do this at this point. Okay, so that's the Helton-Vinnikov theorem. Now this is the worst slide of the talk. So this is a very technical slide, but I still wanted to put this up to show you another way of sort of how big matrices come about. So let's go over this, suffer through this slide quickly. So I'm going to define a convex semi-algebraic set as follows. So I look at pairs x in R to the n and d, a real number, such that the following complicated condition holds. I take d times the matrix A0 plus a linear combination tk ak. This says positive semi-definite. So this linear combination should be a positive semi-definite matrix whenever the tk, the t's, are sandwiched between the smallest and largest eigenvalue of some auxiliary matrices. And so, again, the AI are constant symmetric matrices of some size, n0 by n0. lambda min and lambda max are the minimum and maximum eigenvalues function, and then bk is a symmetric nk by nk matrix whose entries are linear forms in the x's. So this is a bit complicated, and you have to take a moment to parse the quantifiers. But what happens is that the minimum, the smallest and the largest eigenvalue of a matrix, well, those are convex and concave function. And the fact that these functions are concave and convex, respectively, makes this into a convex set. So it turns out that this is a convex set, and we have a theorem with Ni that says that this set is actually a spectrahedron. So there is an LMI of large size, matrix of size n0 times n1 times nm, and this is constructive. So there's an explicit algorithm that you can run in Mathematica, where you have the small matrices AI and the small matrices Bj, and then you apply some tensor operations, tensor sum, tensor product, and you make big matrices. And one reason I show this is because this is one way to derive these ellipses, right? So the multifocal ellipses are a very, very, very special case of this. So if you take the matrices AI to be the 1-by-1 matrix with entry 1, if you take the BKs to be these little 2-by-2 blocks whose eigenvalues are the distance to the point, and then you apply this complicated construction on the previous slide, well, then you get exactly the ellipse. So the ellipse, the parametric ellipse xyd that satisfy this. So it boils down to this expression. So this is a general construction of which the ellipse is a very, very special case. Now the ellipse, of course, is sort of a charming math example, but turns out that these are called matrix cubes. They're actually important in control theory. So in control theory, there are situations where you're very much interested in sets like this to derive stability results, and that was really sort of the real motivation. But I'm showing this because this is how we built the matrices for the ellipse. So let me recap. So for the ellipse, right, it's a convex set. It satisfies the Helton-Vinnikov property. So we know by the Helton-Vinnikov theorem that there is a linear matrix inequality, but this matrix cubes construction actually gives you a very simple algorithm for building the matrix. Okay, so let me go over a couple of research questions. So as I said, this is part of an ongoing project that we have with a group of mathematicians and engineers. And here are some of the questions we're interested in. So one question, is there a nice coordinate-free generalization of the chordal matrix completion theorem? So what's that theorem? So suppose you have a symmetric matrix, and I show you some of the off-diagonal entries, but not all. Okay, so I have a symmetric matrix, and you get to see some of the entries, but not the others. So those that you see, I index them as the edges of a graph. Okay, so I make a graph, and if I and j are connected by an edge, you get to see the entry. If I and j are not connected by the edge, you don't see the entry. Okay? So then you ask the question, can you fill up the entries that you don't see to make a positive semi-definite matrix? Can you make that matrix positive definite? Well, there's an obvious necessary condition. Well, the obvious necessary condition is that the principal minors that you see, they better be positive. Right? So that is to say, the clicks in the graph, for every click in the graph, you get to see the full principal minor, so they better be positive. That's the obvious necessary condition. And you can ask, is the obvious necessary condition sufficient? Well, it's sufficient if and only if the graph is chordal. Right? So that's one of many characterizations of chordal graphs. And we would like to understand the geometry of this. Right? So this map of erasing some of the entries is a projection. Right? So I take my ice cream cone, my positive definite cone, I project it into a lower dimensional space, and the goal is to characterize the image. And this is an instance of this, and we would like to have a more invariant understanding of this theorem. It's wide open. I don't know how to classify combinatorial types of spectrahedron. I don't even know what this question means, even in dimension 3. So historically, convex polytopes have been studied since the ancient Greeks, but they came up, in the 50s as feasible regions of linear programs. And that became very, very interesting. And then the 70s and 80s, polytopes were studied in their own right, phase numbers, combinatorial properties. And I think the time is right to do the same thing with spectrahedra. So semi-definite programming is a very powerful method from an applied point of view, but the feasible regions haven't really been studied extensively. So for example, I don't know a quartic spectrahedron. So here's a conjecture. So if I have a 4x4 matrix and I have a 3-dimensional spectrahedron, I know from algebraic geometry that this could have 10 singular points. But I don't know whether you can actually realize those 10. Right? So if I have a 3-dimensional spectrahedron, it always will have these corner points, but I don't know how many you can actually realize. Minkowski sums of polyhedra are again polyhedra. That's not true for spectrahedra, and it'd be nice to have a good representation. Here, these are sort of questions I already talked about. Is there a good analog to the simplex algorithm? Here's one that I like a lot. Can you tropicalize semi-definite programming? So that means the following. Well, you can solve optimization problems, of course, you can formulate it over any ordered field, such as the real numbers. But sometimes it's natural to have some parameters, maybe epsilon. So you might think about having a small epsilon, a parameter, and you want to optimize, over this field. So, well, how do you draw a spectrahedron? How do you actually run, your algorithm? How do you think about the optimal solution? Well, that's pictures that realize this. This is called tropical geometry. So tropical geometry is the art of drawing piecewise linear pictures over, fields like this. Now, linear programming has been tropicalized. There is a nice theory of tropical convex polytopes, but we don't quite know, how to do this in the semi-definite case. Here's a a virus was found. Okay. Can somebody help me to get rid of the virus? Okay. Computing the convex hull of algebraic varieties is very, very interesting. I'm going to illustrate this in the next slide. And there are promising results by Gouveia, Parillo, and Thomas. I'll show this in the next slide. And it relates to work of Lasserre and collaborators on moment matrices, and they have an algorithm for computing the real radical, a numerical algorithm for computing the real radical of a polynomial ideal. So what is the real radical? Well, suppose you have a polynomial ideal, such as the principal ideal generated by x to the 4th, 2 x squared, y squared, plus y to the 4th. So then the ordinary radical, well, the ordinary radical by Hilbert's Nullstellensatz is the set of all polynomials that vanishes at all the complex points. So that's in this case, x squared plus y squared. But you can use the same definition and talk about the real radical. So the real radical is the set of all polynomials that vanish at all the real roots, and that's quite a bit larger, right? The real radical can be quite a bit larger because this variety of these, the common variety of these ideals is just the origin. So the computing the real radical is this task, to go from here to here. Now computing the ordinary radical, the existing symbolic algorithms implemented on all computer algebra systems, but there's a lot of progress now, and there's a numerical algorithm for getting this. Of course, if you run this on algebraic data, you like to round in the end. You like to recover the algebraic information. Yet one more reason to understand the phi function. Okay, so let's look at the convex hull. So here's a little slide that illustrates the problem of computing the convex hull of a real variety. So I have just to illustrate this by way of 2 examples. So let's say we have a little curve. Oops. Okay, guess I lost here. So let's take the moment curve, t squared, t cubed in 3 space. And just to make a compact picture, let's take t to be between -1 and plus 1. So that's a curve in three-dimensional space. And that might be the input. So input to this algorithm is a little piece of curve like this. Output is a description of the convex hull. Well, in this example, the output is an LMI, is a linear matrix inequality. So in this case, the convex hull of this curve is a spectrahedron, and here's the output. So it's the set of all points x, y, and z, where both the sum and the difference of these two matrices is positive semi-definite. Now you see this in the picture. So here in black you have the curve, but then the convex hull, there's sort of two pieces to the boundary of the convex hull, and they correspond to the two cases of this algebraic representation. So this is the kind of thing you would like to do. Now, this is a very nice example, right? Here the convex hull is actually a spectrahedron. That's not generally true, but we can hope that this convex hull is at least a projection of a spectrahedron. So maybe there exists a higher dimensional spectrahedron that will give us a projected representation, and that's usually good enough from the point of view of optimizing. Why do we want to do this? Well, we want to solve, optimize convex functions over these kind of non-convex varieties, right? So that's the motivation. Now here's an example. So this problem of computing the convex hull of a real variety is interesting, even if the real variety is finite. So let me illustrate this. So suppose you have a zero-dimensional prime ideal with rational coefficients, right? Well, it's going to have a bunch of real roots. So maybe the real roots are these red points over here. And the task is to calculate the convex hull of the red points. Now, how would you do this traditionally? Well, you would calculate the red points, maybe numerically, then take the output, put it into a convex hull algorithm, and try to extract, the facial information of this convex polytope. But that's bad, right? Because you cannot even write down the red points exactly. These have algebraic coordinates. So you're forced, to do a floating point computation or something like this along the way. Now, using semi-definite programming, we can try to go directly from the ideal to the convex hull. Namely, we can hope to take the convex hull of the real variety and write it as a spectrahedron over Q rather than as a polytope over R. So that's an interesting case. It would give us a representation of this polytope over the ground field without actually writing down the facet inequalities, which would require us to go to a field extension. So this is sort of makes sense geometrically. Maybe here you have to have a little bit of an algebraist's point of view. But as I said, so even if you have finitely many points, it can be advantageous to write the polytope as a spectrahedron. Okay, so the next slide, is the conclusion slide. So there's sort of two conclusions. So the first conclusion is for applied mathematicians. So if you're an applied mathematician and if you're a SciAm member or think about being a SciAm member, so as I said, there's a special interest group in algebraic geometry. Now, if you're a pure math student, here's the quiz for you. So this is for students in algebraic geometry. Well, this picture that I showed is a smooth cubic surface. And one thing that you learn about, it's a singular cubic surface. So one thing that you learn about the smooth cubic surface, it has 27 straight lines on it, right? Every smooth cubic surface over the complex number contains 27 straight lines. Now, writing down these straight lines is intimately connected to the determinantal representation of the cubic polynomial. Essentially, every cubic polynomial in x, y, and z can be written as the determinant of a 3x3 matrix of affine linear forms, and knowing that matrix means knowing the 27 straight lines. Now, Cayley, in an 1849 paper, was interested in the question, what happens if the matrix is not a general matrix, but a symmetric 3x3 matrix? What restrictions does that impose? So Cayley was interested in cubic surfaces where the determinantal representation is given by a symmetric matrix. Now, that is exactly the situation we have here in semi-definite programming. And he showed that there must be 4 singular points. And the quiz for the algebraic geometry students is, how many straight lines are on Cayley's cubic surface? Of course, I could leave it at this, or I could say there's 30 seconds left and I can give the answer away. So maybe I will give the answer away and go maybe 1 minute over time. The answer is 9. So there's 6 straight lines that you see, right? So the 6 edges of the tetrahedron give you 6 straight lines. And there are 3 more straight lines at infinity, all the way out, where the elephant ears, touch infinity. They make 3 more lines. So you have 9 lines. Actually, these 9 lines are triple lines. So 3 times 9 is 27. And maybe let me end by drawing the picture. I hadn't planned that, but because Robin had this picture yesterday, Robin Hartshorn, so let me draw the picture the way you would see this picture in an algebraic geometry class. So in an algebraic geometry class, the cubic surface is gotten by blowing up 6 points in the plane. But to get this symmetric representation, you don't blow up 6 general points, but what you do is you look at the intersection points of 4 straight lines in the plane. So look at the configuration of 6 points that you get from 4 lines, and you blow up those points. So this is the picture that you see. So there's a blow up that takes us to this picture. Well, you can see when you blow up these 6 intersection points, they become the 6 edges of the tetrahedron. And then the 3 lines at infinity, so they are the images of these lines. So there are 3 lines through that involve only 2 points. So they become straight lines. So those are the 9 lines. Now what happens to these lines, right? So when you, what happens to these lines? Well, as you blow up the points, these red lines, the 4 red lines, they get carried along for the ride, and they get blown down. They become the vertices of this spectrahedron. So this is the algebraic geometry picture. This is sort of the convex picture in 3-dimensional space. And it's the interplay that's very interesting. And as I said, there are lots of open problems. Thanks for your attention.